Hi, this is Jose Luis and welcome to another video in this series, Introduction to Parametric Modeling. In this video, I would like to discuss advanced topics on data tree manipulation because in the previous videos we have seen how to manipulate lists, so how to work with lists at the tree level but not change the structure of the data tree. But at the same time, we have also seen the two most basic operations about how to change the tree structure, which were flattening and grafting. And you're going to be using them like 80% of the time. Those are the most popular by far. However, sometimes we will need to do way more fine-grained control manipulations at the level of the data tree. And therefore, we will need to have special tools in order to do that. If you go to the tree, if we go to the sets tab, and we go to the tree category, we can see that there are a lot of components that do many things, such as like offsetting branches, retrieving branches, blah, 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 whatever. But in this tutorial, I would like to focus on one particular component, which is going to be the PathMapper, which to me is like the Swiss Army knife of data tree manipulation within Grasshopper. So this is going to be specifically, a lot of what I'm going to be talking about today is going to be very specific about Grasshopper in particular and data tree structures. In other programming languages or in other environments, things work a little different, but it's going to be a super, super useful tool to discuss in this series. And especially, it's going to be useful because we're going to be using it in the next few examples that I'm going to be showing. Now, what is the PathMapper? So if you remember, you have seen me rant a long ago about how I like the expression component because it's very flexible and allows me to customize exactly all the operations in a very elegant kind of one-liner way. So to me, the PathMapper is kind of the expression editor for data tree manipulation. It has a very, very similar spirit, and actually it shares like a little bit of the underlying code actually on the back end, as you will see very soon. The PathMapper is if you will, an editor that I can use to customize the operations that I do on a data tree. So what does that look like? Well, I can plug in here the PathMapper, and then what I can do is I'm going to just plug in here a couple panels so that I can take a look at the structure of the data, and you can see that we're already familiar with this surface that has been subdivided in 3 collections of 4 points each in the UV directions, okay? And then what I'm going to do is I'm going to paste another component here, another panel, and I'm going to plug it in here. Because the PathMapper right now is empty, you can see that there's no operation, have been no changes whatsoever to the data tree. But of course, we are going to change that a little bit right now as we double click on the PathMapper. And as we do that, we get this pop-up called the Lexer Combo Editor, which again, if you will, this is kind of a text editor that it allows me to customize the combinations or the changes that I do to the data tree. How is this going to work? Well, on the left-hand side here, what you can do is you can type in a generic way what the structure of the data tree looks like right now. And then here on the right-hand side, also in a generic abstract way, and I will explain what that means very soon, I can write down an expression of that exemplifies how do I want to change that data structure. So what does that mean? If I look at what's coming in, you can see that what's coming in is basically a tree that has 3 levels, 1, 2, 3. The first 2 levels only have zeros, but the last level has a number that goes from 0 to 1. So representing this data tree in an abstract way is just as simple as opening and closing curly brackets, and then inside of it using variables to represent the level of each tree. So for example, if we have 3 levels, I can say whatever the number of the first level is, I'm just going to call it A. Then I'm going to write a semicolon because that's how they're separated. The second level, whatever that number is, I'm going to call it B. All right, and I'm going to add another semicolon. And whatever the third number on the, whatever the number on the third level is going to be, I'm going to call it C. So I'm just giving it names. I could also name it first, second, third, for example. Actually, let me do that. First, second, and third. Actually, now I'm just going to go for A, B, and C because I find it a little bit more elegant. Whatever. So A, B, and C are going to be the names that are going to be given to the number of each one of the levels. And then what I would like to do here is I would like to write an expression that uses those variables to change the data tree. So for example, the first two levels are pretty boring because they're all zeros. So, but the last level is much more interesting because it has numbers that change from 0 to 2. So let's say that I wanted, for example, to offset all the branches by 1 unit. What I could do is I could say the target structure that I want has to be the same number for the first level, the second number for the second level, and whatever the third number for the third level is, just add 1 unit. And then let me close the curly brackets. If I press OK, you can see that the expression editor now shows here with the expression that I just typed. And also the tree, you can see that it changed from 0, 1, 2, it changed to 1, 2, or 3. So I can also do, maybe I can offset like 5 units, and now you can see how the branch is 5, 6, or 7. I can offset it negatively, for example, like this, right? And then it just goes back 1 unit, etc., etc. So with this expression, I have been able to take a canonical or an abstract definition of the tree with variables A, B, and C, and then represent the change that I want using those same variables and adding like a little bit of a mathematical expression to it, a simple algorithm. All right. What else can I do? Well, let me just copy paste all of this and I'm going to move it here. And for example, I can do things such as instead of adding 1 unit, I can double the number for the branch. So for example, I can say that is going to be 2 times the value of branch C. Okay? And if I actually, wait, let me show you something. If I do a similar operation, but instead of 2 times C, I do 1 plus 2 times C, you can see that the first was 0, 2, and 4, and now it's 1, 3, and 5. And take a look at this. If I were to now combine on an additional panel, for example, if I were to combine on a panel the first data structure here and the second one with the shift, you could see that because the numbers of the branches are now correlative, when they move into the branch here, you can see that they get ordered right away. And therefore, this data goes first, this data goes second, this list goes third, this list goes fourth. And therefore, implicitly, what I have done is that I have woven the branches of the tree one after the other on a one-to-one basis, like 1, 1, 1, 1, 1, something like this. Can you see my face or my? I don't think you need to see my face, but can you see my fingers? How this panel here, has woven with the other one. All these branches have woven like this, which it's a really, really neat thing to do, for example. So by doing a little bit of algebraic manipulation of the data tree, we can do operations such as, for example, weaving 2 data trees that have a similar structure. We can weave their branches. Another thing that I would like to, for example, highlight is that pretty much as the expression editor, the Lexer combo editor allows for advanced mathematical expressions. So if you remember from the expression editor, if we double clicked and we went to the expression functions, we did get this kind of pop-up that gave us a bunch of functions that we could use to calculate numerically, for example, advanced operations such as sines, cosines, square roots, absolute values, etc., etc. So these functions, these expressions, I can use them as they are in the PathMapper. So they are compatible. They use the same lexicon. So for example, here I can say I want the third branch to be now the power of the base number to the power of 3. So the cube of that number. So 0 stays 0, 1 stays 1, and 2 goes up to the value of 8, right? Or, for example, I can say I can use conditional expressions. So for example, let me copy and paste all of this here. So if you look at here, you can see there's a small function called if, which says that the first part is going to be a test, and then if this is true, it returns the A, otherwise it returns B. So for example, here I could write I could write a condition if I open and I close parentheses, and then the first argument is the statement. So for example, if C is equal to 0, and remember that this expression editor uses single equal signs to compare things together, as opposed to, for example, many programming languages that use double equal signs. This one uses single equal signs. So you just need to remember that. And if C equals 0, then the branch name is going to be -1. I'm just going to hard code that. Otherwise, the branch is going to be, the level is going to be the value of 1. And if I do that, you can see that, what just happened? So here by doing that, because I hard coded well, let me just do this first. So this is going to be C. So you can see that if the branch had the last level 0, then we turn it into -1. Otherwise, everything else stays with the same value. Okay? So I will explain what I just did in the next example. Now, what else can we do with PathMapper? With the PathMapper, we can do many other operations that are here common to the tree operations. So for example, let me show you one. I'm going to copy and paste this here. And very often, for example, we have the problem of branches having a lot of redundant information. So all these leading zeros, sometimes are just like, it just gets too big, it's kind of complicated. And actually, many components, what they do is that when you right click, they incorporate an option that is simplification, which if I do, you can see that the tree right away gets simplified into, and it removes all these leading zeros and everything that is kind of useless. So we can do we can do the exact same operation at the path level. So how would that look like? Can you think about this? I'm going to give you 1 second. You can pause the video if you want. So if what we want to do is remove useless levels that only have redundant information, like the first 2 levels only have zeros, then we have represented the first 2 levels with A and B. So the only thing that we need to do is, in the output, just don't use A and B. We only want branches that have the value of C in them. By doing that, we have effectively simplified the tree, like that. All right. What about very common operations that we already know, such as, for example, flattening? Flattening, if you remember, meant taking the whole tree structure, removing all the branches and all the complexity information, and ended up with one single branch that had a 0 and with all the elements in the same list. What does that look like here? Well, turns out that we have used variables to represent the numbers that are coming in at the levels of the paths. But it turns out that there's actually no real need to use that on the target. What we can say is like, whatever you're giving me, whatever the data structure here is, I don't care. What I care is that the structure of the output has to be one single branch. Everything has to be mapped from whatever you were here into this one new branch that is going to have the value of 0. And if I do that, the PathMapper automatically takes every single of the items and just in order feed it to this new branch called 0 that is not respecting or incorporating at all any of the logic of the incoming data tree. Therefore, this is a manual way of doing flattening with the PathMapper. What about, well, you probably know where I'm going with this right now, right? So what if I want to do grafting on the other end? Well, grafting is a little bit more complicated, but it's not really that big of a deal. How could we do grafting? If you remember, grafting was an operation where we took the data tree and then we added a new level. And for each level, we created a new level for each one of the items that we had on the list. And if I do that here, so let me graph that tree. If I graph the tree and I compare the grafted tree with the original one, what we can see is that now each element has its own branch. And we can also see is that the branch has maintained the first 3 levels. So for each item is contained in a branch that has the first 3 numbers being the same one as they were before. But the only thing that we have added is added a 4th level that has numbers going from 0 to 3, 0 to 3, 0 to 3, which also, if you look closely, happen to be the numbers that are the index numbers for the original items. So if we want to do a manual graft, then basically what it means, grafting is maintaining the data structure of the levels and adding a 4th level where each element is now on a 4th level which has the value of its index number. That is roughly the high-level idea. How can we do that with the PathMapper? Well, I have said before that when we're using the PathMapper, we can here, conceptually, we can describe the structure of the data that is coming in. But we can do that not only with the curly brackets representing the data tree, but additionally, we can capture the value of the index number of every item by using the parentheses and then using another variable to capture that number. I'm going to use I because I is a very typical name for referring to indices. And then what am I going to write here? I'm going to give you 2 seconds to think about it, pause the video. And then, yes, you probably guessed it already. I would like to maintain the structure of what's coming in. So A, comma, B, semicolon, C, semicolon. And then now the 4th level is going to be whatever the number, whatever the index number of what's coming in, it's going to be. And as I do that, then I'm going to hit OK. And then you can see now how each one of the elements has landed in a new branch that maintains the first 3 levels, and the 4th level is now the index number. Right? So this is grafting manually using the PathMapper. And the last operation that I would like to teach you how to do with the PathMapper is going to be called flipping the tree. Ooh, what does that mean? So let me show you. So if we go back to where we were coming from originally, which is this surface that we subdivided into 3 families of 4 points, remember how when we talked about, I'm going to hide the surface. Remember how when we talked about data matching and blah, 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 I discussed how the operation of components work mostly at the level of lists. So if I now try to create, for example, interpolated curves with the data that is coming from this component, which remember is 3 branches of 4 points each, because components work at the list level, what's going to happen is that this component is going to create 3 curves, each one of them going through the 4 points of this data tree. Correct? Now, you may find yourself in a situation where this is cool, it's good for you, yet for some reason, instead of creating the curves in this direction, in the direction that we have naturally subdivided the surface, we actually wanted to create the curves in this perpendicular direction, or we wanted to have both. We wanted to have a grid of curves in 2D, which is a very common thing to need to do. So how could we do that? So maybe changing this? No, it's only changing the subdivisions. Maybe taking this surface and flipping it and then subdividing it again in the other. It gets a little complicated. So actually, the easiest way to do it is by taking this data tree, and instead of arranging the 4 points in this branch, 4 points in this branch, and 4 points in this branch, we may want to restructure the data tree and have a list that is these 3 points, another list that is these 3 points, excuse me, another list that is these 3 points, another one that is these 3 points. That operation can be done out of the box with a component that is called flip matrix that is coming from the tree category. So what I can do is I can take this, whatever the data is coming like this, I can take that data tree and then I can flip it so that the structure now looks a little different. So now instead of having 3 branches with 4 elements, I have 4 branches with each element. And if you see the first element here, the first element is the second, the first element is the third, and then the second element is the first one here, the second element is the second one here, the second element is the third one here, etc. And if I do that, you can see that now the curves are going in the other direction. And if I plug this in here, you can see that the indices have also changed. This is the first one, second one, third one, first one, second one, third one. So this is the normal, the regular points, and these are the flip points. So, but if we look closely, what has happened here is that basically every element that had an index of number 0 has now landed in a branch that has the last level being the number 0. Every element that had index number 1 has landed in a branch whose last level is that number 1. Every element that has number 2 landed in 2, and every last element landed in a branch whose last value is the value of 3. So in a way, what has happened here is that we have taken values, we have replaced the last level of the tree with the index value of these elements. So if we want to do that operation manually, it's going to be as simple as doing that. So it's going to be as simple as taking, where am I? Taking this input, the input that we have used, so the 3 levels A, B, C, and the index in parentheses, and then probably just removing the third level and using as the third level the value of the index number. So if I do that and I press OK, you can see that now I have the exact same effect. And if I interpolate with a curve with its elements, you can see that all these elements are now going in this direction. And if I use the point visualization, you can see that the distribution of the indices is also the same one: 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, etc., etc. So, that was a lot. So I hope this was not very overwhelming, but this is just to say that the PathMapper is basically one of the most versatile ways that we have of working with data trees in Grasshopper and making operations that affect the level of the tree of data in a more customized, in a more fine-grained way. There are some operations that we still cannot do with a PathMapper, or maybe I don't know how to do them. I'm not entirely sure about that. Like, for example, completely removing a branch or removing elements from a particular branch. I'm not sure that can be done with a PathMapper, but we already know other techniques. to remove elements from a list, etc., etc. So we can rely on those, or we can rely on some other specific components here under the data tree category. So it's always my recommendation that you have no fear to just drop in components, checking them out, see what they do, and it's actually a really, really good way of learning more of how to use Grasshopper. So I think with that, I'm going to leave it here. This was advanced data tree manipulation in Grasshopper using the PathMapper, the Swiss Army knife of data tree manipulation. And I hope this was useful, and it is definitely for us going to be useful down the road in this series for some of the exercises that we will be doing in this series. So if you liked what you saw, maybe like this video, maybe subscribe to the channel, or just say like a couple of words of gratitude in the comments. We're always happy to hear your voice and to get to know each other. Thank you very much, and I will see you on the next video. Bye bye.